compelled to meet virtually. Even then, more than 150 participants registered for this webinar, and on behalf of my department and college, I extend my warm wishes to the participants who have made it to the webinar today. Before we begin, I would like to request all of you to keep your microphone and camera in switch off condition, and please do not present anything on the screen. The presentation tab is for only the speakers. Now I want to call upon our esteemed chief patron, our principal sir, Dr. Somen Chanda, for his welcome address. Dr. Chanda is a constant inspiration for us. He always motivates us to do better for our college, for our students. This webinar is a part of that effort. Over to you, principal sir.
Thank you, Liton. And thank all distinguished guests, speakers, audience, dear colleagues, students, and ladies and gentlemen. A very good evening to you all. Today, the Department of Electronics, in collaboration with the IQAC, is going to organize a webinar titled Emerging Trends in Electronic Science. My best wishes to the organizing team. Ladies and gentlemen, we all know that the term electronics has been derived from the term electron, a fundamental particle of nature. So electronics is a subject in which dynamics of electrons under the influence of field or potential is studied, either in vacuum tube or in solid state materials. Initially, in 1904 or so, these were offshoot of the studies in physics, but later on, the uniqueness in the behavior of electrons, discovery of solid state electronic devices, and the vastness of application potential made it a separate branch of knowledge. And this particular branch is being called electronic science. Why science and not technology? Because it is an application. Let me explain briefly that it is a science because it searches for the fundamental truths in the behavior of electrons in smaller and smaller spatial dimensions, giving out in return a technology for application devices. When a particular electron behavior is completely understood and hence predictable. Cheap technology has been one of the major thrust areas of research in electronics today. Designing biometric chips, bionic chips or devices, nano chips, and the likes have been attempted, and research is continuing in the world-renowned laboratories with a view of solving various medical, non-medical applications and augmentation of human capabilities. Brain-computer interface is one of these. Classical communication electronics is another arena where a major effort has been put, whence quantum electronics is an emerging field. With the advent of new technologies, new industries are coming into being. Ladies and gentlemen, we all know that power electronics and control electronics play a major role in industries and laboratories. There have been major developments in this particular area also in recent time. We have seen that indigenous developments in science and technology make a nation proud and powerful with a strong economy. If we, the Indian nation, want to be proud and powerful as a developed nation, we have to plan not only for make in India, but for develop in India also. In today's webinar, we all are expecting to satisfy our zeal to know the science behind all these developments in recent time. I hope we can go home with knowledge and satisfaction. With these few words, I welcome you all once again in this webinar. Today we have three eminent speakers from the field of discussion. Our first speaker is Mr. Anupam Das. Mr. Das is currently the director of Amakan Induction Private Limited. He is also the director of Institute of Industrial Automation, an institute established to harness the talent of budding engineers and degree course students in the field of automation technology. Mr. Das has obtained his MSc degree in Electronic Science in 2010 from the University of Calcutta. After that, he studied at Institute of Automation Technology Salt Lake. His area of specialization is Programmable Logic Controller or PLC and Supervisory Control and Data Acquisition bus or SCADA. He started his career at EMT Megatherm Private Limited, Kolkata in 2011 as design engineer, and after that as R&D engineer in the same company. He left the company in 2016 to start his own company, Amakan Induction, which later on became a private limited company in 2018. A sister concern, Proton Service Solution, was established by him in the same year at Bangalore, which solely deals with PCB designing. His company, Amakan Induction Private Limited, provides solution on induction furnace technology all over the world with an annual turnover of more than 6 crore in 2020. Topic of his talk is automation in induction furnace. A hearty welcome to Dr. Das. Our second speaker is Dr. Debra Gangopadhyay, postdoctoral research scientist at the IOCB Institute of Organic Chemistry and Biochemistry, Prague, Czech Republic. Dr. Gangopadhyay is currently working as a postdoctoral research scientist at the Biomolecular Spectroscopy Group, Institute of Organic Chemistry and Biochemistry, Prague. He obtained his PhD in 2017 from the Raman Spectroscopy Laboratory of Professor Ranjan Kumar Singh at Banaras Hindu University, Varanasi. During his PhD, he also worked at the Raman Spectroscopy Laboratories of the University of Jena, Germany. After completing his PhD, he was awarded the National Postdoctoral Fellowship by the Science and Engineering Research Board, DST, India. With this fellowship, he worked as the principal investigator of a project at the University of Lucknow. He then moved to Prague in 2019 through the IOCB postdoctoral program. Dr. Gangopadhyay has deep expertise in Raman, SARS, ROA, UV visible, FTIR, Fourier transform infrared, and steady state, as well as time domain fluorescence spectroscopic techniques. His primary research interests include Raman and SARS based reaction monitoring and sensing of biologically important molecules. Topic of his research talk is in vitro reaction monitoring and sensing by advanced Raman spectroscopic techniques. A hearty welcome to Dr. Gangopadhyay. Our third speaker is Dr. Subhadip Chakraborty, DST Inspire Fellow, Department of Electronic Science, University of Calcutta. Dr. Chakraborty is currently working as a DST Inspire Fellow in the Department of Electronic Science, University of Calcutta. He has done his master's degree in physics from Benares Hindu University and BSc Physics Honours from ABN Seal College, University of North Bengal. He was awarded DST Inspire Scholarship during his undergraduate and postgraduate studies prior to be selected for DST Inspire Fellowship to pursue postdoctoral studies. His research interests include biomedical physics and engineering for clinical applications, design and fabrication of bioelectronic devices, rapid quality assessment of bioconsumables, etc. He has been closely associated with several biomedical projects funded by the World Bank, DST of India, and West Bengal Department of Information Technology and Engineering as an independent research fellow and presented his research in several prestigious international and national conferences and symposia as a contributory speaker. He has published 14 research papers in highly reputed international journals, 8 conference papers, and 1 book chapter during his research tenure. For the last 6 years, he has been working as an integral part of the digital microfluid and nanoscale device design research group led by Professor Sanatan Chattopadhyay in the University of Calcutta. Topic of his today's talk is Genesis of Lab on a Chip devices for electronic biosensing. A hearty welcome to Dr. Chakraborty. I'd also like to take this opportunity to thank the organizers, convener Dr. Liton Balo, HOD, Electronics, and IQAC for giving me the opportunity to thank you
sir,
all.
for your welcome
So
address.
thanks.
Now
And
I
now over
request
to Professor Liton
Mr.
Balo.
Anupam Das for his presentation. Thank you, sir, for your. Over to you, Mr. Anupam Das. Now I request Mr. Anupam Das for his presentation. Over to you, Mr. Anupam Das.
Thank you, Dr. Liton Balo, and obviously Dr. Shomen Chanda, Principal Fakir College, to give me that opportunity to present the present scenario or present situation of the industries, specifically in terms of steel industry. What we can see basically, and which is very important for the students who are now undergoing through that education, where they can they can think about to join that industry. Actually, this industry is not that much of very common industry to the students, because we know very much that after graduating or after completion of education, students normally try to go to that software companies or any soft skill companies, but this is the industry where students can go and students can enhance their knowledge and their experience. And hope all the students from the college, all of you are well, and thank you all to join today's webinar. My subject is basically automation in induction furnace. To proceed about that automation of induction furnace, we need to know what is furnace and where that furnace is being used. That we have to know. Furnace is basically we use in specifically steel industries where steel products are being produced, mainly TMT bar, and except the TMT bar, TMT channel, angle, and then pipe plants are there, and except that mild steel or MS products, we have separate kind of products based on steel, which is basically alloy, not MS. So manufacturing of these steel items, we require furnace. Now my part or my company's part, what we are manufacturing basically induction furnace. There are some other furnaces also, like we have arc furnace, we have blast furnace, but we are manufacturing induction furnace. I am not going into the technicalities of induction furnace, what is induction process and what is all. I think you know or you will know about that, what is the induction. I'll try to highlight some points of induction furnace, specifically the automation part. Before going to the automation part, I would like to present one just small video of making TMT bars. Hopefully I can show you the presentation.
Sorry to interrupt you, sir. You have to present your screen first. Okay. Okay, sir. Okay.
Yes, sir. Yeah, just hold on. I'm just trying.
Yes. Yes, it is visible now.
Is it visible, that video?
Yes, it is.
That video is visible, right? Okay. Okay, so what we have seen, uh, the manufacturing process of TMT bars from we call ingot. That ingot has been manufactured from that induction furnace. Actually, that video is from one of our customer where we have given 8 metric ton induction furnace. Now, what is the global impact of that steel and impact of that furnace, that induction furnace? Basically, in India, if we say, in India, around 1.5 billion metric ton steel item being manufactured per year, and this data is according to the steel market .org 2020, and 30% of crude steel manufacturing been produced by that induction furnace. That means the large amount of steel being manufactured by induction furnace, and the customers of steel basically also prefer that induction furnace because of some reasons, because of pollution reasons, because of the price and the maintenance part. There are some several points uh, for that that steel manufacturers prefer that induction furnace. Now we now come to the point that furnace consists of some points, some items for that for manufacturing of steel. Like we require furnace, we require CCM or continuous casting machine, we require rolling mill for making that TMT bar or channel or angle. Now, if we say that furnace automation, we have a normally automation means we know that PLC drives SCADA and all, but in furnace automation can be done by the microprocessor also, and eventually we are using microprocessor for automation of furnace. Earlier we used analog circuit for automation. Now we are using FPGA for furnace automation, where we have closed loop control system for the limiting part, for the tripping part, and for the control as well. Now we come to that CCM part. CCM is continuous casting machine, where we can produce the TMT, we can produce the ingot for the TMT bar. For CCM, we have to use PLC because we have to control the water pressure, as well as we have to control the temperature of the molten metal, because CCM is the equipment where that molten metal will be treated, and from molten metal will produce the ingot from that machine. So in that CCM, lot of automation we use, and in that automation the basic part is closed loop control system for water cooling, because we have to cool that uh, molten metal, and it becomes uh, a solid ingot from that molten metal. And for that I can tell you the metal temperature when it already melted, the temperature will be around 1650 degrees centigrade, and after treatment of that molten metal from CCM, the temperature will be around 700 to 800 degrees centigrade. Now we come to the rolling mill part. Rolling mill part is fully automated because it is not possible to handle 800 or 700 degree temperature ingot manually. So the total process from ingot to TMT bar, that total process is been automated via PLC and via drive. Basically, we have to control the speed, the temperature, the density of the metal, and the length of the metal, where we have to give the proper shape of the TMT bar from the ingot. Now, if we come again to the furnace part, when that melting process is going on, at the time it is not possible to handle all the things manually. Like we have to pour the scrap into the furnace, and that furnace actually very huge in volume, so it's not possible because high voltage and also high power is being used to melt that scrap, that metal scrap. So we have to use automated pusher, we have to use automated lifter for that scrap, and we basically use electromagnet to lift that scrap and to pour those scraps into that furnace. And after pouring, we have to use the automated pusher, which has been controlled by the PLC and the drive, and definitely we have to use the SCADA. SCADA is the thing where we can communicate uh, uh, this is actually a communication medium, and we can communicate with the processor, you can say, and we have to program both the PLC and both the SCADA. SCADA, we can, in terms of SCADA, we can use HMI, we can use computer, and when like we have to put the weight of the metal, so at that time because we can confine the weight of the metal, because if the weight of the metal will be higher, there will be a chance of accident, because that furnace has a limited access of weight. That I am not going into that part very deeply, because there are lot of points where we can understand which is the limiting point of the furnace. And secondly, the total process, this total control process, it is being controlled by electronics. Now because it is closed loop control system, we need to have a feedback, proper feedback from the output, which is in terms of current or voltage or frequency. So for that feedback part, we have to have very clear circuit, very clear feedback circuit, so that we can control the total machine, we can control the total thing very smoothly. Now there is one another part which is very important and which plays very important role in the furnace, which is pollution system. Because manufacturing of metal is a system or a manufacturing process where pollution will be there. So we have to control the pollution part, and because of that pollution control, we have to use the automation in terms of drive, in terms of PLC and SCADA also, because we have to use PLC and SCADA to maintain the pollution system. This is one type of suction system where that pollution has been controlled, and we can collect the pollution in a in an industrial bag, we call pollution bag, in terms of dust. Now I want to present one another video where you can see the live operation of induction furnace. This is that electromagnet. This is the furnace platform. This whole process, this melting process and that pouring process, all been controlled by PLC and SCADA. Even in this case, the overhead crane also been controlled by PLC. This is the crucible, we say, where the scraps has been melted, and you can see the molten metal. This furnace actually we have given to a customer in Raipur. This is basically 8-ton furnace. 8-ton furnace means at a time we can melt 8 metric ton metal. So if you have any question, if you have any query on that induction furnace or induction furnace automation, you are free to ask me. Whatever I have, my experience or my knowledge, I can share with you.
Okay, I think nobody has question because most of them are students and they are seeing this furnace for first time. Yeah, so I think they have a lot to process and with different terminologies and new concepts. And I am thanking you because now the government is also planning our education to such a point or in a direction that
Yeah,
our students can employ
for the first
themselves
time,
in
exactly.
different industrial
Maybe.
aspects. So
Yeah.
I think your presentation will help them to design their future better.
Yeah.
So I thank you. And Okay, thank you,
Yeah,
sir,
thank
and
you.
I hope to see you in our college
Thank you
with
very much. I
interacting
also
direct
wish
interaction with our students, and
all
so
of the
that
students
you can share more
uh,
experience with them
for
in
their
industrial aspect, I think.
future and
So
future prospect.
Devashis will
Hopefully, they will
definitely be in
choose the
your
right
touch.
way in their
And
life.
with this, and now I call upon Dr. Debraj Ganguly for his presentation. Debraj, over to you.
Hopefully. Okay.
Yes, Debraj. Yes, yes, yes. You're audible.
Hello, can you hear me? Yeah, okay. Okay, so I'm very happy to be here in this webinar today. Mm, I have a very old friendship with Dr. Balo since our PhD days in BHU in Varanasi. And when he invited me to deliver this talk today, mm, there was no option. I had to give it. So I will be presenting something related to my current research work, which is primarily based on Raman spectroscopic techniques. And I will discuss two particular applications of Raman spectroscopy that I'm working on. The first application will be reaction monitoring, and the other one will be sensing. So I will try to keep the talk as
Yes,
elementary
yes,
as
definitely.
possible so that it's easy for the students to understand. And if they find it interesting, they can Google the terms and check how things are done using Raman spectroscopy. So can I move to the presentation now? Okay. So I will just
Okay, I think Debrajda is back. Oh, um, yes, yes, it is visible now. Debrajda,
so can you see my screen?
one moment, Debrajda, your presentation is gone now. Did you
Okay,
stop your presentation?
thank God.
Please
Okay,
check present
so
now, and then your entire screen you will
as you all
show.
know, the topic
That will
of
better.
my presentation is in vitro reaction monitoring and sensing by advanced Raman
Your entire
spectroscopy.
screen. Yes, yes, it is coming up. Now it is
Present now,
visible. Okay.
your entire screen.
No, it is going away. I don't know
Okay,
why. It should not be like that.
is it visible now?
In fact, whatever you are seeing in your screen, we should be able to see it. But
But when I am opening PowerPoint, is it still visible?
I think
Yeah.
developer is clicking on stop sharing button.
No, I haven't. I am still sharing, but as soon as I open this PowerPoint, I don't know why it's gone.
okay, let's wait for a minute. It's coming up. Now we can see your Google Meet page.
your entire screen.
No.
Share.
No. Yes. Now it is visible.
It's shared
Okay.
now.
Yes. It is now. Yes. Okay. Carry on.
Yes, and when you can see I'm clicking on. Can you see that I'm clicking on the PowerPoint? Is it visible? Is it visible now? So there was maybe some technical error. Okay. So as you know, the topic of my presentation today is in vitro reaction monitoring and sensing by advanced spectroscopy and advanced Raman spectroscopic techniques. So right now, this is my workplace where I do my research. It's the Institute of Organic Chemistry and Biochemistry. It's based in the beautiful city of Prague in Central Europe. And I'm working here for last 1 year. Before that, I did my PhD from Banaras Hindu University in Varanasi. And after doing PhD, I was there working as postdoc for 2 years in Lucknow. Then I moved to Prague here in this institute. This institute has a variety of research work being done in this institute. And there are 3 clusters, the Chem cluster, the Phys cluster, and Bio cluster. As I have PhD in physics, so I'm working in this Phys cluster, and my group is molecular spectroscopy. My primary research interest is in the field of Raman spectroscopy. And ever since I started doing PhD, I'm working in this field. I think most of you have some idea about Raman spectroscopy, that it is based on the Raman effect that was discovered by Sir C.V. Raman, for which he was awarded the Nobel Prize. And a Raman spectroscopy is based on studying and analyzing Raman spectra. And the spectral analysis can give us an idea about the chemical composition of any material in molecular level. I will come to that later. I will say about 2 different aspects of Raman technique. One is Raman spectroscopy, the other one is Raman imaging. In spectroscopy, we study such spectra, and we can get information about any sample at distinct positions. And imaging is when we do it in a spatial manner, that is, an entire sample can be scanned and the spectra from different regions of the sample can be obtained, and we can get spatial information about that particular sample. So these are 2 aspects of Raman. The Raman spectroscopy is carried out using this instrument called Raman spectrometer, which has an incident source of light. This is a laser source normally used, and then a focusing system through which the laser is focused onto the sample through a microscope, and then the scattered radiation is detected by a detector, and we get the Raman spectrum. Okay, I have worked on different Raman spectrometers. These are the Rayleigh Raman spectrometers that I operated when I was working as a PhD student in BHU. And then when I was working in Germany, I used a somewhat advanced Raman spectrometer in this university. And right now in Prague, I'm using 2 different Raman spectrometers equipped with 2 different lasers. This is one, and this is other one, which is also capable of measuring some Raman optical activity. I will not get into that. First, I will discuss that how does light interact with matter. So this is the most elementary thing that we all probably know, that when light interacts with matter, there can be different phenomena. There can be reflection, it can be refracted, there can be absorption in the sample and a part can be transmitted, there can be scattering, and there can be emission. So different phenomena give rise to different kinds of spectroscopy. The Raman spectroscopy is primarily based on this scattering phenomena. And the other phenomena such as emission gives rise to fluorescence, and absorption gives rise to UV visible spectrum or even infrared spectrum. Well, so Raman spectroscopy is a kind of vibrational spectroscopy. So you know, all molecules have specific vibrations. Suppose here is a very simple molecule. It can have different kinds of vibrations within its bonds. So these vibrations have some energy. So this energy is stored in these vibrational energy levels within the molecule. And I have shown two electronic levels. If there is an electronic transition within the molecule, we get some radiation which lies in the optical or the UV ultraviolet range. But if there is a transition between the vibrational levels, it lies in the infrared region. So these vibrational transitions give rise to two spectroscopic techniques, that are infrared spectroscopy and Raman spectroscopy. And there are even smaller levels which give rise to rotational transition, and these fall in microwave region. Well, so the Raman effect takes place due to scattering phenomena that I already mentioned. And this scattering can be of two types, elastic and inelastic. So when there is elastic scattering, the incident radiation and the scattered radiation, these have the same energy, or are having the same frequency. So this kind of scattering is called Rayleigh scattering. And if the frequency of the scattered radiation is either less or more than the incident radiation, it is called Raman scattering. So this effect was discovered by Sir C.V. Raman, and the amount of scattered photons that are inelastically scattered is very low. That is 1 in a million or 1 in 10 million photons are scattered inelastically. So the Raman effect is very weak. And therefore, we need highly intense radiation for studying this. That's why we're using laser. Okay, so how does a Raman spectrum look? A Raman spectrum looks like this. We have different peaks at different positions. These are called the Raman bands. And one particular band corresponds to a vibration. Suppose in this region, the Raman spectrum is shown as, in x-axis we represent the wave number, and in y-axis we represent the Raman intensity. So in this wave number region, 2500 to 3500, we get different Raman bands which correspond to the CH stretching, NH, the stretching vibration of this bond, then some OH stretching vibrations lie in this region. In the region between 2000 and 2500, we get vibrations that correspond to triple bonds. And in region that corresponds in between 1500 to 2000, we get different vibrations corresponding to double bonds. And below that, we get many delocalized modes, which are different for all molecules. So no two molecules will have the exactly same Raman spectrum. That is why Raman spectrum is called as the fingerprint of a molecule, and we can distinguish all molecules by observing just their Raman spectrum. Well, there are some disadvantages of Raman spectroscopy as well, but first let me talk about the advantages. It is very sensitive to small changes. It is non-destructive. It requires very limited sample preparation. The analysis of the spectrum can be quite quick if you are experienced doing it. And it is suitable for aqueous solutions, that is, solutions in water. But there are some limitations of Raman spectroscopy. It has a very small detection limit. Detection limit as in very low concentrations cannot be detected by Raman spectroscopy. It is obscured by fluorescent signals. If the sample is highly fluorescent, then the Raman spectra, the Raman bands being very weak, cannot be observed within the fluorescence background. And it is not very suitable for dark samples because dark samples don't scatter light very effectively. Well, what is the use of Raman technique? It is useful in several fields, like in biological sciences, agricultural sciences, medical, geology, pharmaceutics, material science, forensic science. Everywhere Raman spectroscopy has got some use. Some of the major uses are like in detecting or sensing specific compounds that I will discuss in my work, and in structural characterization of new compounds. So if you have some new compound, you want to know the structure of that compound, Raman spectroscopy is very effective in doing that. In studying interaction of molecules or reactions that I will also discuss, that is also part of my work. And observing structural changes, this is also part of my work. And monitoring chemical reactions, which is my primary focus. Okay, so monitoring chemical reactions. How can we monitor a chemical reaction or chemical process? How can we observe how the process is taking place using Raman spectroscopy? That is a very challenging task, and it requires very precise experimental techniques. So this is what I have been doing for many years now. That is in situ reaction monitoring by Raman probe. And we observe the Raman spectrum. We just initiate a chemical reaction, and the reaction is taking place, and we just observe the changes that take place in the spectrum with time. And we see, we can relate those changes with the structural changes that are taking place during the chemical reaction, and we can just monitor the process, what the process is occurring during the reaction. Okay, so, and we can also observe the reaction intermediates, such that the reactant and the product, but what is happening in between, that we can visualize using this Raman spectroscopic technique. Okay, so this is one reaction, the in vitro creatine to creatinine cyclization that I had monitored. This is just, I've put for example, but I will discuss this, one of my recent works. This is on observing the ring formation of N-acetylcysteine, which is a multi-purpose drug, which is an antioxidant, and which is also given to patients, to kidney patients, to control the rising level of creatinine in blood. Well, this is the published paper on this work. Well, for this, as I already mentioned, we have taken N-acetylcysteine, this drug. We made a solution in water, and we made the basic, and we converted the pH of the solution to a basic pH 8, and we started observing the Raman spectra after specific intervals of time. You can see here, we have been observing the spectra after 15 minutes. And we see that after between 120 and 180 minutes, there are some specific changes in the spectrum that suggest that the compound has changed to something else. Well, when we increase the pH higher to pH 9, we found this signature just after 45 minutes, between 45 and 60 minutes, that there are some changes which suggest that it is a different compound now. At even higher pH, we observed similar changes, but even faster, just between 30 and 45 minutes. And at pH 12, it was very quick. Between 5 to 10 minutes, we could observe that a new compound is formed. So when there are, in other wave number ranges also, we could find many differences in many Raman bands, which suggested that a new compound is formed at basic pH. But what is the new compound? On doing the thorough spectral analysis, which is a very difficult task, it requires a lot of experience in doing that. But once you know that, you can analyze the bands and you can correlate it with the structures of different possibilities that can take place from this reactant. And we found that this is the product that is formed at basic pH. That is MTCA, which has a thiazolidine ring. This product is formed at basic pH. There is also a possibility of formation of thiazolene ring where this OH is removed, but at basic pH, this possibility can be ruled out because at basic pH, this OH cannot be removed. And so we have this ring as the product at basic pH. So we could, you see, these Raman spectra helped us to monitor this very important reaction, that how this drug N-acetylcysteine gets converted to its cyclic isomer MTCA, having a thiazolidine ring, and it works in our body. Okay, and we could also determine different intermediates. This is, suppose this is the reactant N-acetylcysteine, and this is the product MTCA. But what happens in between? We have determined these different, a 4-step process, how this ring formation takes place. We could determine using the spectral analysis. Well, this is another antioxidant, glutathione, which is a tripeptide. There are 3 amino acids linked by peptide bonds. And this glutathione, this is also a drug, and it's a very effective compound. We have also, because it has a cysteine part in between, we have tried to monitor if this also cyclizes, although this is a more complex molecule than N-acetylcysteine, but we have tried to find if this is also capable of forming such a thiazolidine ring. For that, you see there are different possibilities. There can be a thiazolidine ring from glutathione. There can be a dimer, which is called GSSG, through this sulfur-sulfur disulfide bond. There can be a dimer of glutathione, which can take place, and there can be a thiazolidine ring. But what exactly happens at basic pH? For finding that, we have done the Raman spectral analysis, and we could see that there are several changes taking place in the spectra of glutathione as we increase the pH. And by a Raman spectral analysis, as the one I discussed before, we found out that the more stable compound and the more the strongest possibility is that glutathione is converted to its cyclic isomer having a thiazolidine ring at basic pH. Well, so this is what I was discussing about Raman spectroscopy. These are the applications of Raman spectroscopy, how by observing the spectral changes, we can monitor a chemical reaction in vitro, that is in the laboratory. But Raman spectroscopy has some limitations. Okay, the main limitations are that molecules with low Raman efficiency cannot be measured, and very low sample concentration cannot be measured. So if a compound, if the sample that I want to measure has very poor water solubility, and we can get a very, very dilute solution of it in water, we cannot get sufficient Raman signal so that we can analyze it using Raman spectroscopy. So to overcome this limitation of Raman spectroscopy, we need to enhance the Raman signal or the Raman intensity. For this, there are several techniques which can be used. There are several advancements by which we can enhance the Raman signal. And one of this, a very important one and a very widely used one, is the surface enhanced Raman scattering, or the SERS technique, which I will discuss in brief. So SERS, I have used the SERS technique for sensing, or also for monitoring some reactions where the solubility of the analyte is very low. I can use this SERS technique in monitoring such reactions. Well, the SERS technique is based on a localized surface plasmon resonance theory, where we use some metal nanoparticles, primarily silver or gold nanoparticles, and these nanoparticles have electric field surrounding these nanoparticles. When these resonate with the incident laser beam, there is this phenomenon called localized surface plasmon resonance, and this phenomenon gives a rise in the intensity of Raman bands, of some of the Raman bands. Okay, and that's why we can get a highly enhanced Raman spectra, which can be studied. Well, SERS-based sensing has been used in sensing several things, including proteins, biomarkers of some diseases, including cancer. It is used for studying gene sequences. It can be used in detecting very small amounts of toxic chemicals and pesticides. It can be used in sensing antigens, glucose, nuclear waste, bacteria, virus, single molecules, and in studying biomolecular interaction. Well, the SERS technique, I have shown a schematic representation of the SERS technique. That is, we have a SERS substrate, which looks like this. You can see there are very small grains of silver put on a glass surface. And these grains are in the scale of 5 to 10 nanometers. And this is a SERS substrate, which we commonly use. It's called a silver island film. And we put a drop of our analyte solution, which is of very low concentration in micromolars, maybe 10 to 100 micromolars. And we put it on this SERS substrate. And this analyte, which is present in the solution, this is adsorbed on these silver particles, silver nanoparticles, and there is surface enhancement when the laser is incident on it. And this surface enhanced Raman signal is detected by the Raman detector, and we get SERS spectra, surface enhanced Raman spectra, as you can see. Well, so this is the silver island film that I was talking about. This is a more uniform grain size, but there should be surface roughness, that the surface thickness shouldn't be uniform throughout the island film. And when we see it under the Raman microscope, we see certain positions where the solution, that is the analyte, is bound or adsorbed on the silver surface. Okay, and we can focus our laser on such positions and we will get the surface enhanced Raman spectra. Okay, so I will discuss briefly about the sensing of creatinine, which is a biomarker. And this is a biomarker in detecting kidney dysfunction or renal dysfunction disease. When a person is suffering from some kind of kidney disorder, then the amount of creatinine in blood increases. So how can we determine the amount of creatinine using surface enhanced Raman technique? This was published in this journal. Well, for this we used a very common reaction of creatinine with picric acid, which produces a dye. So this is called the Jaffe complex, this complex. Okay, so we have carried out this reaction and we have tried to sense the Jaffe complex using this silver island film, which I showed. Okay, so when we see the normal Raman spectra of creatinine, picric acid and Jaffe complex, we see that there is a band in this 700 centimeter inverse region, which corresponds to the ring deformation mode of creatinine. So if we study the Jaffe complex and try to detect this band and observe its intensity, so how can we determine what is the amount of creatinine present in that solution? Well, so here we have done the surface enhanced Raman spectra. I have shown for different creatinine concentrations. You can see these concentrations are in micromolar, and we go down from 150 micromolar to 10 micromolar, and we see that the intensity of this band gradually decreases as the amount of creatinine is reduced. So when we plot it, the intensity versus the concentration of creatinine, we get a somewhat linear pattern. That is, if we can observe, we can just put a solution on the silver substrate, and we can observe the source spectrum. By seeing the intensity of this band, we can directly get, by this calibration curve, what is the concentration of creatinine present. So this is a very comfortable way of sensing the amount of creatinine. Well, there's another way of carrying out the source experiments, that is by using nanocolloids. But for colloids, we need to aggregate the colloids, which is the important part of getting the source spectra. So I will show a somewhat a very advanced technology which we have developed in sensing traces of a toxic chemical arsenic in water. This technology, you can see, we have used 2-mercaptopyridine, which is a very good source scatterer. Normally, we obtain very good source spectrum for 2-mercaptopyridine. And these are the silver nanoparticles. So when we use very small concentration of 2-mercaptopyridine with these silver nanoparticles, we get no source bands of mercaptopyridine, which is surprising, but the reason is known because these silver particles bound with mercaptopyridine are quite far from one another. So we have used another bridge molecule called glutathione, and when we see the source of glutathione at very low concentration, we do not get any source bands because the silver particles are quite far from one another. So when we use both together, glutathione and mercaptopyridine, still we do not get any good source signal because the silver particles are still far from one another. So what we need is to aggregate these particles so that there is sufficient surface enhancement. So for this technique, through this technique, we will try to sense arsenic, as I already mentioned. So when we put some small amount of arsenic, you see, this is the reporter molecule mercaptopyridine. This is the bridge molecule glutathione. You see this mercaptopyridine glutathione, this entire thing comes closer and forms a fine aggregate when we put arsenic in it. And arsenic acts as the aggregating agent, and we get excellent source spectrum for mercaptopyridine. So you see this we have shown as a sandwich model, where these are the silver particles, and this is the reporter molecule, that is mercaptopyridine, because mercaptopyridine produces very good source signal. So we want to observe the source signal of mercaptopyridine. And we have used glutathione as the bridge molecule because through glutathione, it will get attached to the arsenic, which is our analyte, and this aggregation of the colloid will be achieved, and by this aggregation we can get the excellent SIRS spectrum. Now, depending on the concentration of arsenic, this aggregation amount will vary, and the more arsenic, we will get stronger SIRS intensity. So we can directly correlate the concentration of arsenic to the intensity of SIRS band, and we can just precisely determine the concentration of arsenic present in the solution. Well, this is one technique which is a very important and a very effective sensing technique for sensing very small amount of arsenic. We were used to detect about 1 part per billion of arsenic by using this technique. Well, so this was about SIRS-based sensing. Right now, I'm working on this process of amyloid fibrillation. You see, proteins, there are several proteins in our body, and these proteins are normally folded in a particular order so that they function properly. But if there is misfolding in the protein, this misfolding can give rise to formation of amyloid fibrils. That is, these proteins accumulate and form a fibril, and this fibril can be very toxic in nature. So there are different proteins like the amyloid beta protein. When this misfolds and forms amyloid fibrils, this gives rise to some neurodegenerative disease called Alzheimer's disease. And from alpha-synuclein, the fibrillation of this protein gives rise to Parkinson's disease. So there are many such proteins which form fibrils, and these fibrils are toxic. So by this surface enhanced Raman technique, we try to detect this process of fibrillation and small amounts of amyloid fibrils, and we are also trying to detect or sense the reaction of some of the inhibitor molecules which can inhibit this process of fibrillation. That is, we can try to stop the process of fibrillation and thereby just solve the problems created by such amyloid fibrils. This is my current area of research. With this, I will come to the end of my presentation. I would like to acknowledge some of my mentors from different
thank
universities
you, Debraj,
who have
very enlightening speech.
guided
I
me
think
throughout my
students had
research
lots
so
to
far,
process,
and some of
and
my
they can
colleagues
see
who have
how
worked
Raman
with me on these
spectroscopy
projects,
can be
and
used
some of the funding
in different
agencies who have
sensing
provided
mechanism. I
financial
think
support
in
during my
near
research.
future we'll see many
So I'm
portable
thankful to all
devices
of
or
you for
sensors
your attention.
for arsenic detection
Thank you.
or even blood protein or anything, everything. And this work, I think, will lead the path. And I remember working with you in maybe in different lab, but you were working day and night in Raman lab while I was in solid state ionics lab. So there are many memories of hard work. Uh,
Yes.
okay, and I think if anyone has any question, they can put it in chat box. Till there is no question, I think they surely will do some Google some terminology that you have used and various application aspect. And surely, I think
Yeah,
it will be an
we have
introductory
many
for them.
wonderful memories
What is
from
Raman
VHU.
spectroscopy and how
Yeah.
this can be used in a different detection technique, I think. So with this, I would like to call upon our next speaker, my dear friend Subhadip Chakraborty, and
Yes.
over to you, Subhadip.
Yes. Then they can learn a lot of things, a lot of applications.
Yes, yes, yes. You are audible, loud and clear.
Yeah. Okay.
Okay. Am I audible? Hello. Okay. Okay.
Yes, yes, it is visible. Okay.
So are the slides visible now? Okay. Very good evening. First of all, I would like to thank Principal Sir for his kind introduction, and I would also like to thank the organizers of this one-day international webinar, and little clarification regarding the annotation for my name. It's still Mr. because since I have submitted my PhD thesis and yet to receive the degree, so for that period of time it is Mr. Subhadip Chakraborty. So the title of the talk is Genesis of Lab-on-a-Chip Devices for Electronic Biosensing. So this is the layout of the talk, which is divided into two parts. In the first part, I will introduce the biosensors, and we'll see several types of devices for biosensing, may it be MOS or MIS devices, or they may be nanostructure modified devices. So at that point, I will very briefly discuss some relevant results, and in the second part, I will introduce the basic concepts of digital microfluidics as a superior strategy to improve the performance of these fabricated devices. So we'll focus on the integration of this digital microfluidic scheme with these fabricated devices towards approaching our targeted lab-on-a-chip devices. So what are biosensors? In simple language, biosensors are analytical devices that converts any biological or physiological phenomena into a measurable electrical signal by the sequential operation of bioreceptor, transducer, and the detector. Now let us look at the global scenario of biosensing-based researches. Now, from the two graphs, it is quite evident that there is a substantial growth in this domain of research from both academic and industrial perspectives. But in spite of this growth, there are several issues. The most important of them is its widespread commercialization, that is, to make these devices accessible for different stratas of people in our society. Now, these biosensing devices can be categorized either on the basis of bioreceptors or on the basis of the transduction techniques. So, since we are dealing with electronic biosensors, we will mainly focus on the electrochemical or the electrical transduction techniques. So, on the conventional sensing parameters from electrical perspective, we have dielectric constant as the most fundamental property of any biological material. And proper knowledge of this particular property enables us for subsequent measurements of several other properties such as impedance, capacitance, current, etc. So each biomaterial has a unique dielectric property or unique dielectric permittivity, and by monitoring the variation in that property, that dielectric property, we can monitor or we can sense the relevant biological molecules or biological constituents. So this basically opens up the possibility for the incorporation of electronics to measure the biological samples or biological constituents from both qualitative and quantitative perspectives. Now, let us again look into some numbers. So it is quite clear and quite evident that we are going to witness a huge growth in the global biosensor market share in the coming years. And this growth is most likely to be driven by the continuous technological development or advancement in point-of-care electronic systems for diagnosis. Now, what is leading us towards this field of research? So, especially in countries like ours, disease monitoring is a very major issue. The primary constraints in this context include limited communication systems, lack of infrastructure, inefficient manpower, and restricted access to resources for pathological facilities. So in this scenario, we need systems which are capable of point of care measurements, which are flexible, they must be portable, and they must be highly sensitive. And most importantly, we have to achieve all these goals in a very low cost. So this basically paves the way for lab on a chip based point of care diagnostic systems. So in this point, we can define lab on a chip devices formally as the compact form of group of devices that provides analytical information about biological components in a very small dimension. In simple language, in a lab on a chip, we perform the work of the entire lab. So several measurements of different work tables from an entire lab can be confined into a very small dimensional chip, hence the name laboratory on a chip or lab on a chip. Now, before developing these miniaturized devices, we should always develop a prototype system for the same measurements. So, from this figure, it is quite clear that the prototype measurement system is nothing but a parallel plate capacitor immersed into a biological sample, liquid sample, which is kept in a simple glass test tube. So, the circuit is also quite simple. You can see here there are two capacitors CDL, which are known as the double layer capacitors. They are formed on the electrode surface, that is, on the interface of the electrode and the biosample. And this R sol and C sol, this resistance and this capacitance, they generate due to the virgin electrical nature of the biological sample under investigation. So you can easily calculate the equivalent impedance from the circuit of this circuit, and you can have its frequency spectrum. So in the lower frequency region, you can see this CDL dominates the overall impedance of the system. This frequency independent part is due to R sol, and in the higher frequency range, we have this portion dominated by the C sol. So depending upon the type of sensing, the type of biospecimens, we monitor these three regions. For example, for bacterial sensing, we monitor the interfacial property of the electrodes. Hence, for that case, we check this low frequency region, and in contrast, for any carbohydrate sensing or saccharide sensing, we generally monitor this high frequency region. Now, this is the on-wafer device that we fabricated in our lab. From the steps of fabrication, you can see the device is fabricated by shadow lithographic technique. We have a clean silicon surface, then we deposit silicon dioxide as a dielectric layer on by ALD technique, and with the help of a stainless steel mask, we replicate an electrode pattern on the substrate. So you can see here the device, and the sample is put on the device, and you can also see here the equivalent circuit. Now, we have studied this device with some biological samples. So first we did studies on lymphocytes, that is the white blood cell. We conducted this studies with the collaboration with SSKM Hospital. So we took samples from one normal person, one diabetic person, and one patient who was suffering simultaneously from diabetes and high cholesterol. The case is known as diabetic dyslipidemia. So from microscopic images, it is quite evident that there are morphological differences in this kind of cell. So we have tested this cell suspensions in our device, and we found a distinct variation in electrical properties of these three types of cells, and for the first time, we reported a correlation between an electrical parameter and the glycated hemoglobin, that is HbA1c, which is often referred to as by the doctor to have an idea of the average of your 3 months glucose level of your body. So this entire study generated a couple of papers. Now we shifted from white blood cells to red blood cells, and we tried to detect anemia with the help of our devices. And from here you can also see a strong correlation between the electrical parameters and the hematocrit level, which is also almost proportional to the hemoglobin level of our body. So we also studied this relation, and I'm not going into the data analysis part since the time is short. And so this one we studied. This one is was quite interesting a study. So our red blood cells have a discoid biconcave discoid shape generally. So in certain physiological conditions, this type of discoid shape tend to take a spherical shape. So in general, in case of chain smokers, a study just showed that their red blood cells are more prone to take this perocytic shape. Okay, so what happens there? So this situation is known as perocytosis, and when your cell gets a spherical shape, it becomes more prone to rupturing. That is, you become more vulnerable to anemic diseases. Okay, so here also we can see distinct variation for the electrical properties for these two types of cells. So all these studies were performed using the fabricated device. So in the next step, we further move towards a point of care device. So what we did, we had a small impedance measuring IC embedded on a small evaluation board. So we use this IC instead of this entire benchtop analyzer. So this reduced the overall dimension of the measuring system, and we obtained a similar trend of electrical parameters, which was similar as that we obtained with the benchtop analyzers and also with the commercially available chemoanalyzers that we use in pathological laboratories. So up to this point, we have seen some microelectrodes for biological sample measurements. So now, for measuring electrical properties of biomolecules, so what do? We modify those devices with proper nanostructures. Generally, we use nanowires. So this eventually increases the sensitivity of the devices. In our lab, we generally use zinc oxide nanowires for biosensing. Since they have high surface to volume ratio, they have high contact area with the analyte, they have high isoelectric points, the toxicity level is very low, and they are easily functionalizable. So we fabricated this nanowire-based flexible glucose sensor, and you can see that the dimension is quite small, and you can also see the strong relation, the strong correlation of the electrical parameters with the glucose concentrations from these two calibration curves. We also bended the substrate for up to 40 degrees and observed negligible variation. So we can say that these devices can be used not only on flat surfaces but also in bended surfaces such as our skin, tongue, and etc. So up to this, we have seen several devices and their performance. So in this part, I will talk about the basics of digital microfluidics and its integration with this device. So microfluidics, what is microfluidics? Microfluidics is basically the behavior movement and control of microliter droplets. Okay, so behavior of liquids in micro regime, they differ greatly from the macroscopic properties such as surface tension, laminar flow, diffusion, etc. So by exploiting this property of liquid, we can do a large number of things, and hence this is truly a multidisciplinary field with a variety of applications. So the microfluidics can be categorized in two types. The first one is continuous flow, or the analog microfluidics, in which the micro droplets are moved by creating a pressure gradient within micro channels with the help of micro pumps. So here you are moving the micro droplets with the help of pressure. But in case of digital microfluidics, here we manipulate the droplet digitally. So that's the beauty. And it has a huge application in present day biomedical engineering and medical device fabrication. So here you can see an array of electrodes, and by applying proper sequential voltage, we are moving this droplet. So the entire operation is done digitally. Now, almost all of us, I think, know about surface tension. Surface tension can be treated in a couple of ways. First, as stored energy per unit area, or this can be realized as the tangential force per unit length. So, from the concept of surface tension comes the concept of contact angle, which is the angle formed at the triple point, that is the intersection of three interfaces, that is the solid liquid, solid gas, and the liquid gas interfaces. And the contact angle can be calculated with the help of the famous Young's law. Now, when the contact angle is acute, the surface is known as a hydrophilic surface. That is, if we dispense a liquid drop on the surface, the liquid drop tends to spread on the surface. But when this contact angle is greater than 90 degrees, the surface is known as hydrophobic surface. So in this surface, the surface has an inherent tendency to repel a mass of water. That is, if we dispense a water droplet on a hydrophobic surface, look, this takes a sessile form, and the contact area of the interface becomes less. Okay, so the more the more hydrophobic is the surface, the less will be the interfacial contact area, and hence less will be the interfacial frictional force, and hence less will be the actuating voltage that we will use to move this droplet. Fine. So now we will see the basic principle of action of this kind of microfluidic devices. Here we have an open system and we have a closed system. So for now, for convenience and simplicity, we will deal with this open system. So what we have a couple of electrodes here, and on the electrodes we have a dielectric layer. So we use this dielectric layer to prevent the electrical breakdown of the device. And then we have a hydrophobic layer here. I have already told you the importance of this hydrophobic layer. And then we put a sessile drop on the hydrophobic layer, which eventually forms the contact angle. Now what we do, we ground this first electrode and apply a voltage on the second electrode. And then we will see this droplet will start moving towards the charged electrode. So by applying controlled sequential voltage, the droplet can be moved accordingly. Let us go into a bit detail. Now you can see here there are 4 electrodes, and a sample droplet is placed in such a position that is its center of mass remains on the first electrode. In this situation, we ground the first electrode and we apply a positive voltage on the second electrode. Upon the application of this voltage, there will be a potential difference, and when there is a potential difference, there will be a flow of free charges inside the sample droplet. This flow of free charges will consequently give rise to an electrical pressure on the droplet meniscus, and this will create a force, and this will eventually change the contact angle of the droplet. You can see from the schematic. As the contact angle changes, the droplet starts bulging towards the second electrode. And as this bulging continues, the center of mass of this droplet shifts towards the second electrode, and after a certain time, when the center of mass shifts completely on the second electrode, we have a quanta of droplet movement. So when this droplet is now on the second electrode and partially on the third electrode. In this situation, we ground the second electrode and apply a positive voltage on the third electrode, and this will consequently move the droplet further. And by this way, by applying sequential voltages, we can further move the droplet to a particular direction. Okay, so the thing is, let us now imagine that at the end of this electrode array, we have a sensing device that we designed, and you have seen those devices previously. So our task is to take this droplet, to drag this droplet with the help of the sequential voltage towards the sensing chamber. So we have here a single type of droplet. So we can similarly fabricate several other electrode arrays, and we can move the droplets of multi-specimen liquids. So this is the beauty of digital microfluidics, that it enables multi-specimen droplet testing. So in general devices, we don't have this facility. So you can measure several types of biological samples simultaneously in this device. So I have already discussed the basic physics. So as we apply the potential difference, it will create a force on the droplet meniscus, and this force can be calculated by integrating Maxwell stress tensor over any arbitrary surface which surrounds the droplet. Right. So now what we did, we simulated the device in console software, and you can see here, by the application of voltage over time, you can see there is a shift of this droplet along the charge electrode. So the movement is quite clear. Now, to fabricate these devices, we follow certain experimental steps. Now, the fabrication mainly follows standard lithographic steps, such as you can use optical or photolithography, or you can use offset lithography, printing lithography. This kind of lithography techniques are generally used. Once we fabricate the device, we coat a hydrophobic layer on the device, and then we place the liquid droplet on the device and apply sequential voltage that moves the droplet, and we record that movement under microscope and camera. So this is a very small documentation. This was taken, I think, almost a couple of years ago in our lab, and you can see the applied voltage here is 5 volts. So actually, this is the goal. We always have to reduce the actuating voltage or applied voltage. So if we can reduce the applied voltage to 5 volts, we can control the drop by microcontrollers easily. So I'm just playing the video here. Now, on application of the voltage, you can see the bulging. The bulging has started, and there's the movement. So it is a quantum droplet transport, and similarly, by fabricating such electrode arrays in several positions of a particular device, you can move and you can manipulate samples or droplets for belonging to multiple samples. Fine. Now, this is a fun game actually. I was talking about the hydrophobic layers previously, and this has a huge role in these devices. So we thought that the worldwide Teflon is actually used as a hydrophobic layer, which is quite expensive and increases the device cost. So we thought, why don't you go with the natural route? So while we talk about hydrophobicity, from nature's point of view, two things come to our mind. One is the lotus leaf, and the other one is taro leaf. পদ্মপাতা এবং কুচপাতা সবার আগে যেটা আমাদের মাথায় আসে, because they have beautiful hydrophobicity. So we did the same analysis, SEM, scanning electron microscopic analysis, and you can see here microtubules, which are again composed of these nanotubules. So this actually reduces the surface area of the interface, and this things make these leaves this much hydrophobic. So what we did, we extracted this material and we coated them on silicon substrate, and you can see we almost had a super hydrophobic surface. This was quite good. We almost had a super hydrophobic surface for both the cases. We also calculated the dielectric constants of this material, and it was found to be of the order 21 or 70. But there is a problem which we are trying to resolve. Since they are biowax, so they have a very low thermal stability. So that's the problem. We are just working on this issue to make them more thermally stable. So this is the detailed scheme. We have several types of biological samples. We move them. We move the other type of samples. We mix them, and we further drag them to the sensing chambers, where we finally identify the disease or quantify the problem. So these are salient advantages. We can move the droplets, we can multiplex them, we can mix. The system is automated. Sample requirement is very small. We can precisely control the digital panel, and most importantly, the system enables multi-specimen testing. Now I will summarize. So I actually owe this slide to my supervisor, Dr. Chakraborty. I borrowed this one from him, and we generally do this portion with the people from electronic science. We're working on the sample movement, the sample sensing, and you can see here this is the entire scheme for a lab on a chip. So our collaborators from IT and applied physics, they're working on the signal processing and data generation things. Here we have you have a comparison block where you pre-store the reference values of any biological material for any particular disease, and you compare with your data with the reference values, and finally you do the identification or the diagnosis of the diseases. One more interesting aspect in which some of my colleagues are working, it is the energy management issue. So they're mainly working to make these devices self-driven. Okay, so you can see here there's a lot of work in this area. Particularly, you need biologists, you need physicists, you need material scientists, you need IT people, you need doctors. So there is an enormous scope of research, and I would encourage the young minds to think about this, and if they're interested, they can pursue these things for their further researches. So these are some relevant facilities that we use for this kind of work. In this, we have in CRN and in our Salt Lake campus and Electronic Science Department from Rajabhaja Science College. We have electrical setup for measurement in the frequency range of hertz to gigahertz. The entire range we can measure in our lab. So we have an advanced probe station with low temperature setup. We have an entire electrochemical workstation, and in microscopic we have APACM, we have Biosensing. And for growth and fabrication, you can see here we have the MBE, electron beam lithographic system, optical lithographic, and recently we installed this RF sputtering unit in our Rajabhatta Science College lab. We have a couple of furnaces for growth, and for hydrophobicity monitoring, we have this contact angle
Thank you,
volumeter.
Shubhadip, for your
Now,
very
I
bright
would
and
like to
enlightening
thank my
speech. I think
mentors and
students have an
several
idea, at
funding
least
agencies,
basic
my
idea,
department, my
how the
collaborators,
modern day research is going
and
on. I
most
mean, we need
importantly,
material
last but
scientists,
not the least,
physicists, the people
the
from
organizing
IT and
committee
electronics and
from
all of them.
Fakir College.
And for the
Thank you.
students of electronics, I think lab on a chip concept is total new domain,
So,
and they can see the future of portable devices. And I also like to tell every participant that Subhadip Chakraborty is not only a scientist, he is a very fantastic and amazing human being. He is also a poet. He have done many comedy show also, and he is a dear friend. And I remember whenever we meet, we discuss about our researches in detail about dielectric spectroscopy and etc. And this takes our friendship in whole new level,
okay.
I think. And thank you, Subhadip, again for this lecture. Okay, I think we are at least at end of our event, and I would like to request Dr. Bonali Vishas of our college to give vote of thanks to our speakers.
Yes, well,
Bonaladi, over
that's
to you.
very kind of you for these things. I often hear these things, but it's nice to hear from you.
You are audible. You are audible.
Thank you.
ওকে রিটার্ন শুনতে পাচ্ছ? I really enjoy the talk and thanks that you give me this opportunity to give vote of thanks to the audience. Respected Chief Patron Dr. Shomen Chando, Principal of Fakir College, Convener Dr. Liton Balo, Assistant Professor, Department of Electronics, Fakir College, Joint Convener Debraj Dattagupta, State-Aided College Teacher of Department of Electronics, Fakir College, and all the audience, students, ladies and gentlemen. It's my pleasure to have been asked to propose a vote of thanks on this occasion. I, on the behalf of the Department of Electronics, Fakir College, and on my personal behalf, extend a very hearty vote of thanks to all of the speakers for gracing your important work and sharing with us your finding and opinion today. I would like to express our sincere thanks to Mr. Anupam Das for giving us very interesting coverage on automation in induction furnace. He is a director of Institute of Industrial Automation and Embedded System, Amakan Industries Private Limited. And he presented us two videos. In first and in second videos, he showed that an electromagnet was carrying the scraps, and I really enjoyed the thing that okay, automation is really needed in this thing, because otherwise if human is handling all these things, it is very dangerous. I guess that for student it is new, all the thing is new, but audio visual presentation at least help them to understand that with science what you can do. And all those terms he used like PLC and SCADA, I also did not know. I just googled all these things, and students also can do the same thing, but at least they knew the word microprocessor, I guess. And he mentioned that in this automation process they are using microprocessor, and it gave the student the basic idea that with all these studies in most of the audience here are student of Fakir College, and they got the idea that with all the study we are doing, there is a way to use it. student always read from the book and they think, okay, I don't know what is the use of all these things. Even when I was in BSc, I was also thinking like that. But Mr. Anupam Dash presented so well that I was also involved in this talk. And then I would like to thank Dr. Debra Gangopadhyay for demonstrating his excellent research work on in vitro reaction monitoring and sensing by advanced Raman spectroscopic technique. Dr. Debraj Gangopadhyay is currently working as a postdoctoral scientist at IOCB, Prague, Czech Republic. I was fascinated by his work, and he mentioned so many techniques, so many graphs. Maybe it is hard for student to understand. Again, I am saying this thing, but I really enjoyed very much. After a long time, I enjoy this talk very much. And he mentioned that SEARCH technique, surface enhanced Raman spectra, that technique can be used to detect at different kind of disease also, and arsenic in water. And he mentioned all this, all his work very elaborately, and I understood very well. And I wish him very best for his future work. And lastly, I wish our sincere gratitude to Mr. Subhadip Chakraborty for sharing his cutting edge research on genesis of lab on chip devices for electronic biosensing. He is a DST inspired fellow, Department of Electronic Science, University of Calcutta. He just said that he submitted his PhD thesis, and I wish him very best for his PhD viva. He is doing a very excellent work. Also, he showed many data, many graphs, and on his presentation, page 15, he showed that their fabricated device is very small compared to the device used nowadays. So this is very new work, and he also showed that ACM image was showing that there is a difference between all the blood cell, like normal people blood cell, healthy people blood cell is showing different thing, and some infected people blood cell is showing different image, and those images can be correlated with the data he got from the fabricated device. That is very excellent thing to do, and I hope that students also enjoy his talk very much, and we all the audience, I think our principal and everybody enjoyed very much. And I again thank Dr. Liton Balo, Mr.
Thank you,
Devashish
Bonaldi,
Dasgupta,
for
and of course
brilliantly
our
summarizing the whole
principal
session.
for
And I would
organizing
like to inform all the
this
participants that
one day
feedback link
international
will be
seminar
emailed to a registered email ID,
on this
and you can have
on
your
recent trend on
e-certificates within
electronics
7 days from now.
science.
And
And thank you very
I would
much.
officially like to conclude
And
this session.
I
And
again thank everybody,
stay
and
well,
have a
and
good
what I can
evening.
say in this pandemic situation, stay safe. Thank you all.